Do you have any questions? The last time I think we just I already talked about the variance, right? And how to compute the variance, and then some property of the variance values, right? Correct. So I think this is what we learned last time. Let me share the file with you. Can you see it? Can you see it, everybody? Okay, so this is what we learned last time, right? The variance of x, the definition for the definition, the variance of x is the mean of x minus m squared, where m is the mean of x, right? That is what we learned last time. And then we come up with the computational formula Vx equal to the second moment minus the square of the first moment. And then you can find, and then we have this formula for the variance of x of ax plus b, which is a squared times the variance of x. The constant b doesn't have any effect on the balance, okay? And you get the standard deviation of ax plus b. If x and y are independent, then we have the variance of x plus y equals the variance of x plus the variance of y. You should notice that if you have the mean of x plus, then it is always the mean of x plus the mean of y. You don't need the independence of the two random variables x and y, but if you want to find the values of the sum, you need the independence of the two variables to be able to get this equation. Okay? Do you understand? Is that all clear, everybody? Good, right? Let's have a look at the following example. There's a chance that a bit transmitted through a digital transmission channel is received in error. And suppose that x is the number of bits received in error of the next four bits that you transmit. You have the following probability mass function, and then you come up with this table. Okay, I think we already we are already showed how to get all these values, right? 0.4 is the mean of x, and 0.36 is the variance of x. Now I want to discuss on the last column. What is the last column? The last column gives you the value, the values of x squared times f of x, where f of x is the probability mass function of the random variable. And you come up with a number 0.52. What is that? This value is the sum of x squared f of x. And do you remember? This is simply the mean of x squared, correct? Okay, so I can say that the second moment is 0.52. Then I can use the formula, say that the value of x is the mean of x squared minus the square of the mean of x. And that is 0.52 minus 0.4 squared. Okay? And that is 0.36. Do you understand? Is that all clear, everybody? Is that okay? All right. Now let's consider this example. Suppose that the density function is 0.05 for the range 0, 20. Can you find the mean and the variance? Can you get the answer? Okay. You can see that in this problem, you have the density function f of u equals 0.05 in the interval 0, 20. Okay. Then the mean of x is the integral from 0 to 20. And then u times f of u du. And that is the integral from 0 to 20, u times 0.05 du. Okay. And then you come up with 0.05 u squared over 2 from 0 to 20. And that is 10. Okay, we can do the calculations to get that answer. How about the variance of x? The variance of x is the integral from 0 to 20, u minus the mean value square times f of u du. Okay, and then you can do the calculations to get 100 over 3. All right, there is another ways to get the answer. You can find the mean of x squared. Find the mean of x squared, which is the integral from 0 to 20, u squared f of u du. And then you get the integral from 0 to 20, and then u squared times 0.05 du. All right, you get the answer 400 over 3. All right, then you can find the variance as well. In this way, you get the mean of x squared minus the square of the mean of x. And that is 400 over 3 minus 10 squared. So you still get the same thing. Is that all clear, everybody? Okay. Now let's have a look at the following, the next example. In this example, we can find the variance and the mean value. In this example, we don't have formula. We only have the graph. Can you tell me which one gave you the greatest sum of the mean and the standard deviation of x? Can you tell me which one give you the greatest value? Which one gave you the greatest sum? The orange one. Why is that? X4. Why do you think that it is X4? Okay, you can see that the mean of x, the mean is the center of the distribution, right? And because you have all these distributions as symmetric, then it should be at the middle of the range. So you can see that the mean of x1 and the mean of x2 should be the same, right? This is x1, x2, x3, and x4. So they are the same and they are 0. For the mean of x3 and x4, you see that they are the same. All right, and they are 30. Okay, so you get this inequality. How about the variance? The variance is used to describe the variation of the distribution. So if you can see that the possible values are 48 far from the mean value, then the variation is big. Otherwise, it is small, right? So you see now you see that x1, x3 they have the same shape, therefore they have the same variation, or let's say they have the same variance values. Okay, so as I'm saying that the variance x1 and the variance x2 and x3 are the same, right? Um, the variance of x2 and the variance of x4 they are the same as well. So and they are greater than the variance of the other of x1 and x3. So based on this, I can conclude that x3 gives you the greatest sum. Understand? Is that all clear, everybody? Should be okay now. May I move on? Let's consider the next example. All right. Now we want to find the value of c by using the equation 1 equals the integral from -1 to 1 c 1 minus u squared d. This will be the function f of u, right? And then you can use the calculator, or you can do the calculations to get the answer, to get it. I will make it quick. Let's say you get 4c over 3. So c must be 3 over 4, okay? And then you can find the mean of x, which is the integral from -1 to 1 u f of u du. And then you get the integral from -1 to 1 u times c times 1 minus u squared du. This function is an odd function on on this domain, on the symmetric domain. That's why I can conclude that it is 0. Or you can use the calculator to get the answer. And then I need to find the values of x, which is the mean of x squared minus the square of the mean of x, right? Well, the second term is 0 already. Now we need to find the first term. In order to do that, I need to find the mean of x squared, which is the integral from -1 to 1, and then I get u squared times f of u, which is c times 1 minus u squared d. Is there any question so far, everybody? Everyone, is that clear? Okay. Now I want to move to the last part of this chapter, in which you need to know, in which you need to deal with a vector. In many random experiments, more than one quantity is measured. It means that there is more than one random variable. For example, if you select a flash unit to check it from a production line, you may want to measure the recharge time and the flash intensity. So you can consider them all together at the same time, right? It means that you need to deal with a vector of two components, all right? And each component is a random variable. You may want to say, why don't we consider each random variable separately? Then we only need to deal with a single function, a single random variable. Well, it is not, it is not that simple, right? Think about the performance of a student in a class. In my class, for example, I need to have a look at the score of the midterms, of the midterm exam, of the final exam, of the quizzes, of the projects, to be able to investigate the performance of a student, right? So I need to consider all of them all together at the same time. I cannot just have a look at the final exam separately, okay? So you need to consider a vector of many random variables, all right? And then you come up with a vector, you call that vector a random vector, all right? And to make probability statements about several random variables or a random vector, we need the joint probability distribution, all right? If you have a single random variable, then you need to consider x minus u, the probability that x equals u, to define the probability function if x is a discrete random variable. If you have many discrete random variables, just like x and y, then instead of using x equals u, I need to consider x equals u and y equals phi. All right, this is the joint event I want to deal with, and I want to find the probability that this joint event occurs. All right, and I call that one that function, the function f of u, like this, the joint probability mass function. Okay, then I have this. I have the following joint probability mass function. Okay, so you get this function f of u v. Now we have the properties that f of u v is greater than or equal to 0. Besides, the sum of f of u v is greater than the sum of f of u v is equal to 1. Okay, that is always 1. Make sense? Let's try the following example. If you have a look at this, you see that you get 0.01. 0.01 is the probability that x equals 1 and y is 1. 0.02 is the probability that x equals 2 and y is 1. 0.25 is the probability that x is 3 and y is 1. Okay, and you have all the 12 values. The sum of 12 values is exactly 1. All right, can you find the following probabilities? Can you do that? Think about that for a minute, please. Okay, let's see. Let's have a look at this. You see that the probability that x is less than 3 and y is less than or equal to 2 should be these two columns to get x is less than or equal is less than 3. So x could be 1 or 2, something like this. All right. And then you get y is less than or equal to 2. You have these two columns. All right. So you come up with these 4 values, and the sum of the 4 values will give you the jump probability. So it gets 0.01 plus 0.02 plus 0.02 plus 0.03. And then it gets 0.08. Okay. For the second probability, I want to find the probability that x is less than 3, given that y is less than or equal to 2. Why is that? It is the John probability. You need to use the conditional probability, and you have to use the definition for that. X less than 3 and y is less than or equal to 2 over the probability that y is less than or equal to 2. Okay, and then you come up with 0.08 for the top, and for the denominator, you have, what is that? You get 0.50. Y is less than or equal to 2, so you get these two numbers, 0.28 plus 0.25. Do you understand? Is that all clear, everybody? Is that clear?
Yes.
Okay. Okay. You can also find the probability that y is less than or equal to 2, given that x is less than 3. That is the jump probability that y is less than or equal to 2, given that x is less than 3, divided by the probability that x is less than 3. All right. And then you can use similar arguments to get the answer. So you come up with 0.2 plus 0.25 for the denominator. Okay. So anyway, you can find these two probabilities without any problem, I think. All right. Now I want to talk about the marginal probability distribution. If you have a look at this table, you can see that from here, I can conclude that x can take the values 1, 2, 3 with probability 0.2, 0.25, and 0.55. Make sense? Do you understand that? All right. And And this is simply the proximate function of a single random variable x, and you call it the marginal distribution. All right, you can definitely find the mean of x and the values of x. The mean of x is simply 1 times 0.2 plus 2 times 0.25 plus 3 times 0.55. All right. And in order to find the values of x, you need to find the second moments. You get 1 squared times 0.2 plus 2 squared times 0.25 plus 3 squared times 0.55. And therefore, we can find the values of x, which is the mean of x squared minus the square of the mean of x. All right, is that all clear, everybody? It is okay, right? Okay. Here's the formal definition for the marginal probability distribution. All right. Okay. All right. Now, I can give you this this one for the marginal distribution. A mobile website is a set from a smartphone. X is the signal strength, and Y is the response time. Again, we just go back to the problem we mentioned before, and we come up with with the two rows, the row, this row and this column. Then the column we call it the marginal distribution for y, okay, because it provides the probability mass function for the random variable y, and the last row gives you the probability mass function for x, and you call it the marginal distribution for x. Okay, it is okay, right? Okay, so we just finished on this chapter. We just finished this chapter of random variables. Okay. And this here is the outline of what we have learned so far in this chapter. Okay, so we learned how to describe the distribution of a random variable by using the CDF, the predicate function, or the density function. Then we learned some characteristics of a distribution, including the mean value, the median, the variance, and the standard deviation. Okay. All right. Let's have a short break for about 10 minutes. And then after that, we will go back to the lecture, to the meeting to learn the next chapter of some special random variables. All right, some special distributions. And we start with the binomial distribution, all right, and then the Poisson distribution. Okay.